Good evening, everyone. We are going to get started. Welcome to the public lecture hosted by KIPAC, the Kavli Institute for Particle Physics and Cosmology. My name is Sinan Du. I am the Outreach and Engagement Manager at KIPAC, and I am also the main host of today's event. It is lovely to see all of you here in person, and we also welcome the online group of a comparable size that is watching the live stream right now. As you can see that we have cameras all set up here. So we're very excited since some of you know that we have been trying to feature public lectures of topics that you are most interested about. And black holes, honestly, it's always been one of the most suggested topics that we gathered from the feedback. And today we're especially excited to present this second lecture of this two-part series on black holes. And today's lecture will be focused on supermassive black holes, which now we think sits at the center of every single galaxy. So before we get started, I wanted to give a big shout out to the entire team who is supporting our event behind the scene. Those include the front desk staff that you have already met, the tech team here, and also Leon, who is helping me with the live stream. And for our online group, we also have chat moderators who will answer the questions as they come in. So I am going to let everybody to say hi very quickly, so all of you can meet them. First of all, we have Zhefu.
Hi everyone, I'm Zhefu Yu. I'm a postdoc in KIPAC, and I will be one of the online chat moderator today. Yeah.
Thank you. Next, we have Haley.
Hi, I'm Haley. I'm a second-year grad student in KIPAC, and I'm super excited to moderate the talk today.
Fantastic. And last but not least, we have Jay.
Hi, I'm Jay Baptista. I'm a first-year grad student in KIPAC, and I'm really excited to hear what Dan has to say.
Well, thank you all. So for those of you who are joining online, you can see the chat box on the right-hand side, and you can put all your questions there, and we also welcome discussions. Most of the questions will be directly answered by the chat moderators who are also subject matter experts on this topic. And the remaining will be saved for Dan to answer during the Q&A. And for all of you joining us in person, you can save your questions during the Q&A at the very end, or if you like, also chat with Dan afterwards once our event has concluded. So now it is my greatest pleasure to introduce tonight's speaker, Dr. Dan Wilkins. So for those of you who have followed KIPAC for a little while, you may know that Dan has also hosted and co-hosted many public lectures in the past. And so today I'm especially excited that he's going to be wearing his black hole expert hat and also be the speaker. So Dr. Dan Wilkins is a research scientist at KIPAC Stanford. His research primarily focused on supermassive black holes, and especially studying how the matter falling into the black holes can power some of the most extreme events we see in the universe, and how these supermassive black holes can also play an important role on the formation and evolution of cosmic structures. Aside from doing research, Dan is also involved in developing the next generation of space telescopes, working with NASA and the European Space Agency. So Dan got his PhD in astronomy from the University of Cambridge and was awarded a very prestigious fellowship called the Einstein Fellowship from NASA, which brought him to Stanford afterwards. So Dan is extremely passionate about science and communication. He gives regular public lectures, has appeared on TV and radio. And one of my favorite fun facts is Dan has hosted planetarium shows and stargazing events, even on cruise ships. So that I think is one of the best places you could hear a science talk. Yeah, so without further ado, let's welcome Dan.
Thank you. So of course, the first challenge is making the technology work. So we work with space telescopes, but Zoom is a whole different challenge. Okay. Excellent. Well, good evening, everyone, and thank you for joining us. It's a real pleasure to be here to talk to you about a part of science that I'm very passionate about, very interested in, and that is the study of supermassive black holes, what they are, how we can find them, and how some of these supermassive black holes can put on some spectacular firework displays for us to watch, and what that means for the universe that we live in. Now, gravity is the force that binds our whole universe together. It is holding us right now onto the planet Earth. It holds the planet Earth and the other planets in orbit around the sun. And it binds together the stars that make up a galaxy. But what happens when this force of gravity in a region of space gets so strong that it overwhelms everything else and nothing can escape it? Well, we call that most extreme manifestation of gravity a black hole. Gravity is the mutual attraction between every bit of matter in our universe. The strength of that force pulling the matter together depends on how much mass we've got and how close that mass is together. And we can express that with Newton's law of gravitation that tells us that the force of gravity that's pulling together any two objects with a mass is equal to this number we call g, that's known as Newton's gravitational constant, multiplied by the mass of both of those objects, and then divided by the distance between the center of those objects squared. That distance here we're calling r. And as we visualize what a black hole is, a useful thought experiment to run in our minds is that of a rocket launch, trying to launch a rocket from the surface of the Earth into space. If we want to get the rocket into space, we need to launch it at a high enough speed so that it travels away from the Earth faster than that force of gravity can pull it back. And we call the minimum speed we need to launch that rocket at the escape velocity. That escape velocity is higher. We need to launch that rocket faster. The more massive the planet is, and the smaller that planet is, the denser that planet is. So the closer to the center of that planet we are. The bigger the mass of the planet and the smaller the radius of the planet, the higher the speed we need to launch the rocket at to escape the surface and get it into space. But now imagine that we have so much mass compressed into such a small volume of space that this escape velocity becomes higher than the speed of light. Well, this was exactly the thinking of British mathematician John Michell in 1783, and also the French mathematician Pierre-Simon Laplace at around the same time. They were hypothesizing what could happen if you had a star so massive and so small and dense that this escape velocity from its surface was higher than the speed of light. And they coined the phrase a dark star because the light would not be able to travel away from the surface. As light tried to escape the surface, it would be turned around by the force of gravity. We now understand from the laws of physics that the speed of light is the ultimate speed limit. Nothing can travel faster than the speed of light. So if light can't travel fast enough to escape these so-called dark stars, then nothing can. But a true theory that describes what happens at the extremes of gravity, and a true theory that describes a black hole, had to wait until 1916, when Albert Einstein published his theory of gravity, known as general relativity. Now, Einstein's great breakthrough came from thinking of gravity not as a force that exists between pieces of matter, but of thinking of that gravity as a property of space and time itself. General relativity says that any mass in our universe, like a planet or a star or a black hole, creates a dent in space and time. And the force that we experience as gravity is because we are trying to travel through a space and time that is curved. But we can't perceive that curve in space. We just feel it as the force of gravity. Now, the entirety of Einstein's theory is summed up in this equation at the bottom of the slide. So if you understand that, you probably don't need to hear the rest of the talk. But if, like me, you like to see things in pictures, stick with me and we'll pull apart exactly what that equation means and exactly what a black hole is. So building on these ideas of Mitchell and Laplace from the late 18th century and framing them in the terms of Einstein at the beginning of the 20th century, a black hole is formed whenever we have some amount of mass, we'll call that amount of mass m, that's been compressed or it's collapsed into a small enough volume of space that the radius of that object is less than this critical value that we call the Schwarzschild radius. So for some mass m, if we compress it into a size with radius less than 2 times Newton's gravitational constant again, times that mass, divided by the speed of light squared, we will have created a region of space around that object from which no light and nothing else can escape. And we have turned that material into a black hole. Now, just to put some numbers on that, if we had something with as much mass as the sun, we would have to compress it to a radius of just 3 kilometers or 1.8 miles to turn it into a black hole. To turn the Earth into a black hole, you would have to crush it to a size less than 0.9 of a centimeter. But if we can do that, the force of gravity will overwhelm all other forces in that region. The actual material that forms the black hole will be crushed down into the center of the black hole. It will reach extremely high densities that actually defy our best current understanding of the laws of physics. We call that center of the black hole the singularity. But then surrounding that singularity, there's this region of space defined by this sphere of this Schwarzschild radius. And that denotes this zone of space around the singularity that is the point of no return. We call that the event horizon. If we're a long distance away from the black hole, it just has normal gravity like everything else in the universe. But as we get closer and closer, we start to feel the effects of the extreme gravity. And if we get close enough, if we get less than this Schwarzschild radius away from the center of the black hole, we have passed through the event horizon and we are destined to fall into the black hole. There is nothing we can do to escape. And no light, no message we could send could ever get out. But even Einstein himself, having created this theory that predicts the existence of black holes, thought that they were far too weird to ever really exist in nature. Another scientist who we think of as synonymous with the word black hole was also extremely skeptical that they could ever exist from this theory. That other scientist was Stephen Hawking. So how did we come to understand that the weird product of the theory of gravity that is a black hole, a region of extreme gravity in space from which nothing can escape, could really exist within our universe? How could we actually find a black hole? Well, One way we could make a black hole is from a star. For the most of its life, a star, like our sun, is a perfect balance between two opposing forces. Remember that gravity is this mutual attraction between all material. So all of the gas that makes up a star is being pulled together by the gravity. The gravity is trying to crush the star. But the nuclear fusion reactions happening in the core of the star are heating up the gas, and the hot gas that makes up the star create a pressure that pushes outwards, acting against the gravity, crushing the star together. So we have this balance of two forces. But when the star runs out of the fuel that it needs to keep those nuclear fusion reactions going, that heat source that it has starts to run out. So the gravity starts to win. And a star coming to the end of its life starts collapsing under its own gravity. Now, if the star is more than about 10 times the mass of our sun, this collapse is extremely rapid, just from the strength of the gravity from all of the material that's there. And this rapidly crushing material heats up so quickly and releases so much energy in the process that the star can explode as a spectacular supernova explosion. But then, if there's enough material left behind at the heart of that explosion that hasn't been blown away, the force of gravity just keeps pulling it together. The gravity pulls it in, it gets smaller. It gets smaller, so the gravity gets stronger. So it pulls in some more. It gets smaller again. The gravity gets stronger again. It pulls in some more. And you can see where I'm going with this. It keeps going and going. The gravity gets stronger and stronger and stronger. And the leftovers of this star just keep collapsing in on themselves, creating a black hole. Well, the discovery of a real black hole in our universe came with the advent of X-ray astronomy, looking for X-rays, a high-energy form of light, shorter wavelengths and higher energies than the visible light that our eyes can see. The 1960s was a renaissance of X-ray astronomy, with the first X-ray detectors being launched on rockets into the upper atmosphere, and then satellite programs, starting with NASA's Uhuru satellite, putting X-ray detectors into orbit around the Earth. Now, this is the latest image we have of the X-ray sky, taken from the German eRosita mission. This is a recent X-ray telescope launched in the last 5 years that has done a survey of the entire sky. And we can see that scattered all through our universe, the bright band across the center is the plane of our own galaxy, but then scattered through the galaxy and all across the universe around the outside of this image, we see these bright points of X-ray light, almost like stars, but not emitting visible light, emitting X-ray light. And we've since come to understand that many of these bright points of X-ray light are black holes, some within our own galaxy and some scattered far across our universe. Black holes are not just real, having come from this obscure theory to something that could really exist, but they are extremely common. The first one that was discovered was in the constellation of Cygnus. And I'll admit, as astronomers, we're not particularly good at naming things. The first X-ray source that was discovered in Cygnus, we called Cygnus X1. But Cygnus X1 was one of these bright points of X-rays coming from a region of space. And when astronomers first saw that, they were keen to work out what could be producing those X-rays. Louise Webster and Paul Murdin at the Royal Greenwich Observatory in the UK, and Charles Bolton at the University of Toronto's Dunlap Observatory trained their regular visible light telescopes on this patch of the sky. And what they discovered was a massive star. But this was a little bit puzzling, because stars in and of themselves don't really produce a lot of X-rays. So there's something funny going on. On closer inspection, it turns out that this star isn't sitting still. This star is moving in an orbit. We see it traveling round. It must be in orbit around something. But what could this mysterious object be? Could this be a black hole? Well, to produce the energy that's needed to generate those enormous power X-ray emissions that we were able to detect, we need something very compact and very dense in order to be able to release that much energy. We can measure actually how heavy this mysterious object needs to be by measuring how fast that star is traveling and working out how strong the gravity needs to be to hold that star in its orbit and stop the star flying off into space. So we know how strong the gravity needs to be to keep the star moving. We know how much mass we need from Newton's law of gravity and Einstein's law of gravity, general relativity, to produce that much gravity. And it turns out you need about 15 times the mass of the sun here. Now, the other thing to know about Cygnus X1 is that the X-rays flicker extremely quickly. It varies very quickly. And to be able to vary very quickly, it needs to be quite small. The fact that it was flickering, getting brighter and dimmer in its X-rays within a millisecond tells us that whatever this object is, it needs to be less than 100 kilometers across. We actually now know it's more like 10 kilometers across. But our theory tells us that if we have 15 solar masses in a region of space less than 100 kilometers across or less than 10 kilometers across, it must be a black hole. It's the only thing it can be. So Cygnus X1 truly was the first discovery of a real black hole in our universe. So I started this talk by talking about black holes as this region of space from which nothing can escape, not even light. And now I'm telling you that the first black hole that was discovered in the late 60s and early 70s was discovered because it's an extremely bright source of light. So you're probably thinking this guy has no idea what he's talking about. How can a black hole be producing such a bright light source? Well, the answer is the light isn't actually coming out of the black hole. The clue is the fact that the black hole has that star traveling around it. Actually, most stars in our universe don't live alone. Our sun is quite rare in that respect. Many stars are found in binary systems, living out their lives in orbit with another star. And if one of those stars comes to the end of its life before the other, explodes as a supernova, and leaves behind a black hole, what we're left with is a black hole in orbit around a star. And that black hole, with its gravity, tugs the gas from the surface of its companion star. So the material from the companion star is being pulled in towards the black hole. As the material gets pulled in, it forms this flat disk that we call an accretion disk. Accretion is a technical term for the matter joining onto the black hole, falling into the black hole. The gas in that accretion disk, as it goes round and round the black hole, gets crushed together, and it gets heated to millions of degrees. So what we are seeing is not this bright source of X-ray light coming out of the black hole. We are seeing it coming from this superheated material in its final moments as it spirals in through this disk, getting closer and closer to the black hole before finally plunging in through the event horizon. So Cygnus X1 is a relatively small black hole. It was formed at the end of the life of a massive star. It's about 10 times the mass of the sun and about 10 kilometers across. But a parallel story was unfolding in the 1950s and the 1960s, as astronomers, notably those at the Mullard Radio Astronomy Observatory in Cambridge in the UK, started building radio telescopes to explore radio waves emitted from outer space. Those first surveys of the sky with radio telescopes had revealed these mysterious, powerful sources of radio emission that would become known as quasars. The giant Lovell telescope at the Jodrell Bank Observatory near Manchester in the north of England confirmed that these quasars really were very compact objects. And if they're observed just using a regular telescope, using visible light, they look a bit like stars. Hiding somewhere in this image is one of these quasars, as seen by the recently launched James Webb Space Telescope. You probably can't tell which one the quasar is there. It blends quite nicely into the background. It's that one there in the middle. But Martin Schmidt at Caltech in 1963 measured the spectrum of the light, the spectrum being how much light we're getting at different wavelengths or different colors coming from one of these quasars. And he saw the specific colors of light that we expect to see from hydrogen gas. Except the colors of that light coming from hydrogen had been shifted. They were much redder than normal. We know that light from distant celestial objects gets redshifted. Its color gets pushed from bluer wavelengths to redder wavelengths by the expansion of the universe. And the further away these objects are, the bigger this effect. But this object, looking at how much those colors of light from hydrogen had been redshifted, this quasar must be some 2 billion light years away. This is well outside our galaxy. All the other stars in this image that are about the same brightness are in the Milky Way galaxy. This is 2 billion light years away. So if this appears as bright as those other stars, but it's so much further away, it must be hundreds of billions of times brighter. And it was Donald Lyndon Bell at the University of Cambridge who worked out that the only thing that could possibly be powering something as bright as 100 billion suns is the force of gravity. Nuclear fusion is just not powerful enough to produce such a bright source of light. The only thing that can power such a bright source of light is the force of gravity pulling material into a black hole. And this light is powered by that material in its final moments before it plunges in through the event horizon. And these quasars are not black holes like Cygnus X1, around 10 times the mass of the sun. These must be supermassive black holes, millions to billions of times the mass of the sun. Another one of these remarkable supermassive black holes is found in this rather unremarkable galaxy called Cygnus A. There's the galaxy there, as seen with a visible light or optical telescope. It's a pretty big galaxy. It's got a little bit going on in its shape. It's got some dust passing in front of it. It's kind of a big elliptical blob-shaped galaxy, but it's not that special when you look at it in visible light. But if instead we look at this same patch of the sky with the Chandra X-ray Observatory, we see that this galaxy is surrounded by very hot gas, reaching millions of degrees. What is heating the gas around that galaxy? Well, let's now look at this same patch of the sky in radio waves. Radio waves reveal these enormous jets of particles being fired out of the center of that galaxy. These are jets being launched at more than 99% of the speed of light. They travel thousands of times the size of the galaxy, and then they slam into the gas that surrounds the galaxy, where they inflate these beautiful bubbles, heating the gas. Just putting all three, the optical, the X-ray, and the radio image together here, this is actually one of the images that inspired me to study black holes in the first place, trying to understand how a black hole is able to launch a jet close to the speed of light. And that jet is being launched by that material in its final moments, just before it plunges into the supermassive black hole buried at the heart of that galaxy. Well, we've now come to understand that every major galaxy in our universe has a supermassive black hole at its heart. This is the Andromeda Galaxy, our nearest neighbor major galaxy, and there's a supermassive black hole buried among the stars at the heart of that galaxy. And of course, all the best galaxies have one, including our own. This is an image looking towards the heart of our own galaxy, the Milky Way. And if we zoom in on that very bright region in the center of the image, we see a number of stars. The stars in the center of our galaxy are traveling around in orbits. They're actually traveling pretty fast in their orbits. This movie is made from 16 years worth of observations from the Very Large Telescope down in Chile. And the stars right at the center there are going round at 12,000 miles an hour. They must be in orbit around something. Whatever that something is, it must have enough mass to produce enough gravity to stop a star traveling at 12,000 miles just flying off into the galaxy. We also know whatever this object is has to be very small, because those stars just happily go round in their orbits. They're not crashing into anything. So we can work out we need to have 4 million times the mass of the sun compressed into a volume of space that's not much bigger than our solar system. And the only thing that can possibly be is a supermassive black hole. Now, luckily for us, our supermassive black hole is quite quiet. It's not powering one of these bright light sources. It's not a bright quasar. It's not launching these huge jets out. But that's not to say it's completely silent. If we stare at the center of our galaxy with the Chandra X-ray telescope, we can see these flashes of X-rays coming out of the heart of our galaxy. Every time we see one of these flashes of X-ray light, that is probably a little cloud of gas, little bits of material getting too close to the black hole, being torn apart, heating up, before being pulled into the black hole. But in contrast to our own galaxy, the quasars, which are part of a broader group of objects that we know as active galactic nuclei, are produced when there is a continuous stream of material feeding that black hole in the center of the galaxy. Here we can see a Hubble Space Telescope image of one of these active galactic nuclei called Messier 106. The black hole in the center of this galaxy is feeding on material at about 10,000 times the mass of the Earth every year. And as that material falls into the black hole, the energy released is enough to power a light source in the heart of that galaxy that is brighter than all of the stars in that galaxy put together. So as astrophysicists, some of the big questions we're trying to tackle with regard to supermassive black holes are how exactly do they power some of the brightest objects in the universe? What is happening in that extreme environment just outside the event horizon, what is happening to that gas that's falling into the black hole, letting it power such bright light sources? How do they launch those magnificent jets we saw in Cygnus A, traveling at close to the speed of light? How did those supermassive black holes form in the first place? And how did they grow to millions to billions of times the mass of the sun? And how does that enormous energy output from the black hole and the material falling into it affect its environment? How does it affect the galaxy that it's living in? So I'd like to spend a bit of time now telling you how we can get a closer look at exactly what's happening around a black hole to power these magnificent light shows. Well, if we want to take a direct photograph or an image of a black hole that we can actually resolve the event horizon, it's quite difficult. Even for the nearest supermassive black hole, Sagittarius A star, that's the name of the black hole in the center of our galaxy, or one of the biggest nearby quasars, called M87, looking for the event horizon, that region of space from which nothing, no light can escape, is like looking for something the size of an apple on the surface of the moon. To resolve very small features in an image, you need a very big telescope. The bigger the telescope, the better the resolution, and the smaller the objects in the image you can see. To resolve an apple on the moon, or to resolve the event horizon of a supermassive black hole, you would need a telescope the size of the planet Earth. But fortunately, there's a technique called interferometry, where we don't have to turn the whole Earth into a giant telescope, but we can connect together telescopes that are far apart. And if we connect them together in the right way, we point them all at the same patch of the sky at the same time, and we combine the data we get from them, they behave like a telescope that is not the size of an individual telescope, but it's the size of the distance between them. So there's a network of telescopes called the Event Horizon Telescope that are spaced all around the Earth. They stare at the same patch of the sky at the same time. Their data gets recorded onto hard disks. 2 copies of it get put onto 2 separate airplanes. One of them is flown to MIT in Cambridge, Massachusetts. The other is flown to the Max Planck Institute for Radio Astronomy in Germany, where the data from all those telescopes is combined to create an observation as if we had that telescope the size of the Earth. And this achievement is truly spectacular. Pointing the Event Horizon Telescope network at M87, we can see here the galaxy and the jet that's being launched by the black hole in the center of it. We can zoom in right on the central region of that image. And this is not a computer simulation. This is a real image of the hot gas that is around the supermassive black hole in M87. We see the ring of gas. It's brighter on one side than on the other because that gas is traveling in orbit around the black hole. And the dark ring in the center, that is the event horizon. That is the region of space from which nothing, not even light, can escape. And this is the image of the black hole in the center of our own galaxy, called Sagittarius A star. But unfortunately, the Event Horizon Telescope is only actually able to resolve the event horizon in these 2 black holes because of the size of the event horizon and how close they are to us. Can we get a close-up view of a bigger collection of black holes across our universe, particularly those quasars, those ones that are powering the really bright light sources in galaxies? Well, to do this, we can use the fleet of X-ray telescopes we now have in orbit, including the Chandra X-ray Observatory, the European Space Agency's XMM Newton X-ray Observatory, NASA's NuSTAR X-ray Observatory, And I'm very lucky that recently I've been able to work on some of the next generation of X-ray observatories. This is an observatory led by the Japanese Space Agency, but with a collaboration of us here in the US as well, called XRISM. This was launched last August. And then we're planning even the future generation of X-ray observatory called Athena. This is a European-led project that we hope to launch in the 2030s. And here at Stanford, we're actually developing some of the camera technology to enable this next generation of telescope. A large part of my own research is analyzing X-ray observations of supermassive black holes to find out exactly what is happening outside the event horizon that lets them power these spectacular light sources and these jets. There's an impressive storm brewing around the black hole. The gas that's falling into that black hole forms this disk. It swirls around, getting crushed together and heated to millions of degrees. We can see bright, visible, and ultraviolet light coming from that disk of hot gas. Gas in that disk is whipped up into powerful winds that blow out into the galaxy. And this disk of gas gets so hot that the electrons come off of the atoms. This disk of gas going around the black hole turns into a giant electrical generator. It creates electrical currents and it powers an electromagnet. The rotation of that material and the rotation of the black hole itself twists up the magnetic fields coming from that magnet and turns it into a particle accelerator and produces this region around the black hole that we call the corona. These are electrons that are getting accelerated to very high energies. And if those magnetic fields get twisted up in just the right way, that is how we think the black hole is able to launch those jets of particles traveling almost at the speed of light. Now, one of my favorite black holes, a few years ago, we were studying with XMM Newton and NuSTAR, and much to our surprise, it decided to put on a little bit of a light show for us. It was happily going along, producing the X-rays like it normally does, and all of a sudden, it starts emitting these bright flares, these sudden bright flashes of X-rays, getting brighter and dimmer, brighter and dimmer. And when that happens, we're actually able to see that flash of X-rays and then the reflection of those X-rays off of the disk of gas that's falling into the black hole. We see a flare of X-rays coming from the corona. Then we see the reflection of that flare as it echoes off of different parts of the disk. At different times after the flare, we see this reflection, this echo, or this reverberation, we sometimes call it, coming from different parts of the disk. And what was truly remarkable here is after a bit of time, we see, first of all, this first sweep of reflection come across the disk, and then notice that ring of reflection that's hanging out close to the black hole at the end. We were able to actually see that second echo. We get the first echo of X-rays coming off of the disk, and then we get a second echo of X-rays that we weren't fully expecting to be able to see, but our theory told us it should be there. What we were seeing was the reflection of the X-rays, the echo of the X-rays, off the piece of gas in the disk that should be hidden behind the black hole. We shouldn't be able to see it. But that black hole has curved the space around it. So the light rays that come from the back of the disk are able to travel around the black hole and towards our telescope. That's kind of like you being able to see my feet right now as I stand behind this podium, with the light rays being bent around for your eyes to see. And we were able to figure out that when these bright fireworks went off, this corona, this region of high energy accelerated electrons, jets produced around the black hole was actually being shot away from the black hole, as if this system, which doesn't normally have a jet, was trying to get its own jet started. And of course, when you start talking about things coming out of black holes, the media starts to get excited. This was a headline in one of Britain's finest tabloid newspapers, the Daily Mirror. Now, don't worry about the headline. Radioactive light here is referring to the X-rays. But what I'm particularly proud of, I think, an achievement of my career, is actually starting one of the Daily Mirror's famous surveys. Connected to this article, they asked their readers if they were scared of black holes. And I'm a little disappointed that actually the no's were just winning, but it was pretty close. Now, before we wrap up, I just want us to spend a moment thinking about the awesome amount of energy that can come out of this material falling in to a supermassive black hole. If we just do some simple accounting, we add up all the energy that's coming out in the bright light that we see from quasars. We add to that all of the energy that's being launched out in those jets. We find that the total energy output of a quasar, the total energy output of a black hole in the center of a galaxy while it is feeding, while it is growing, is more than the gravitational energy that is holding the stars into the galaxy. Just think about that for a moment. There's enough energy coming out from around the black hole in the center of this galaxy, if we could equally share it into all the stars of that galaxy, to blow the galaxy apart. Now, we know that this didn't happen because we see galaxies in the universe. We actually think that every supermassive black hole in the universe goes through this phase as a quasar while it is growing. Even Sagittarius A star would have been a quasar in its early days when it was growing. So how could it be a quasar without blowing the galaxy apart? Well, let's think about how a galaxy grows. A galaxy will grow in the early universe from gas and material that's falling in from its surroundings. As gas falls into the galaxy, it becomes part of the galaxy. And some of that gas will clump up and it will form stars. So the galaxy gets bigger, it grows more and more stars. But some of that gas will also go down to the center of the galaxy, where it will feed the growing supermassive black hole. So while the galaxy's getting bigger, the supermassive black hole's getting bigger. And while the supermassive black hole is getting bigger, it's producing this enormous energy output. It's producing bright lights, it's launching these spectacular jets. And we end up with a feedback loop. The energy output from the black hole in the center of the galaxy actually starts pushing away the gas that's trying to get into the galaxy to make it grow bigger. And we can see this happening in the Perseus cluster. This is a collection of about 1,000 galaxies that all live together. They're bound together by the force of gravity. And we'll zoom in on the brightest galaxy at the heart of this cluster. Now, the optical image from the Hubble Space Telescope tells us that this isn't quite a usual galaxy. It's got these beautiful filaments hanging out around it. It's a giant elliptical galaxy with these filaments reaching out. Now, to this Hubble Space Telescope visible light image, let's add the Chandra Space Telescope X-ray image. This shows us in purple here that this galaxy, like Cygnus A, is surrounded by hot gas. And then in pink here, I'm showing the radio waves. We see that in the gas that's surrounding the galaxy, there are these two giant bubbles, one here and one here. Just like in Cygnus A, those bubbles are produced when the supermassive black hole growing at the heart of that galaxy launches out two jets. those two jets leave their energy in that gas surrounding the galaxy, and they inflate those giant bubbles, pushing away some of that gas that's trying to get in to the galaxy. And I think this image really inspires us to think of black holes not just as these great destructive monsters that swallow anything around them. We can instead think of the black hole as a sculptor living at the heart of its galaxy, guiding the growth of that galaxy, pushing away extra material as the galaxy grows, preventing that galaxy from growing too big. And then over time, as that black hole runs out of fuel to feed it, the quasar, the light, and the jets will switch off, leaving behind the galaxies like the one we live in today. And just for comparison, the black hole governing the growth of that galaxy is equivalent to something the size of a grape controlling something the size of the planet Earth. And I'll leave it there, and I'm happy to take any questions. Thank you.
Wonderful. Thank you very much, Dan. That was very informative and just so many great pictures. All right, so we are going to start with our Q&A. Anyone who has a question, feel free to raise your hand. Okay, over here.
Hi, thank you, Dr. Jenkins. Very simple question. Why is the accretion disk flat?
Okay, well, let me also repeat this for the online audience. And actually, there was a discussion of this very single question online. So people would typically think that gravity is just, spherical, right? Like symmetrical. But then why would the accretion disk be flat, that all the matter falling into is just along this plane?
Yeah, that's a really good question. And the answer comes down to one of the laws of physics called the conservation of angular momentum, that says if something starts spinning, it has to keep spinning unless you're somehow able to take the energy out of it, take the angular momentum out of it. So if we imagine we've got our black hole here, and then we've got this big load of gas that's trying to get into that black hole from all directions, it's very unlikely that all of that gas will be perfectly lined up. By random chance, there'll be some of that gas that's moving slightly faster than the others. So the overall motion of that big cloud of gas will be slightly in one direction, but only by a very small amount. So that means that in the beginning, this big cloud of gas starts to rotate almost because some of that gas is just missing the black hole. It starts to rotate very slowly. But as the gravity pulls it in, because we have to conserve this angular momentum depends on the distance squared. So as we bring the gas in, to keep the same amount of angular momentum, it has to rotate faster. So what starts off as this small rotation gets faster and faster and faster as the gas collapses. So you have this thing getting faster and faster, and then all the gas moving around, colliding in all directions. The combination of those two effects cause this big cloud to flatten down into this disk that's kind of like water going down your sink.
Great question. Over there.
Yes.
Oh, yeah. So I guess this question is related to the reverberation mapping as you were talking about the reflection. So can you clarify what you mean by the back of the black hole and how you're able to see light being scattered from there?
Yeah, exactly. So when we say the back of the black hole, what we mean is if we imagine we've got a black hole here, and then there's this disk of gas around the black hole, what we mean is the side of this disk that's on the opposite side to the black hole to us. So for you, there's a bit of disk here, there's a black hole, and then there's a bit of disk here. So the back is this bit of the disk that, to our viewpoint, is hidden behind the black hole. Yes. So the question was that what distinguishes the front from the back? So if you could just fly around the black hole, it would probably look the same in all directions. There's nothing special about one side of the black hole compared to the others. But what distinguishes it for us is that as those photons, as those X-rays travel around the black hole, they have to go through the curved space very close to the black hole around the outside. And this causes their energy or their wavelength or their color, if you like, to get stretched or shifted. So blue light becomes more red as it comes close to the black hole. So by looking at how the color of the X-rays or the wavelength of the X-rays is altered, and then also looking at the time it takes after the flare went off for that part to reach us, because it takes a long time for that light to come all the way around the black hole. That's how we're able to tell it apart from the reflection in front of the black hole.
Well, thank you. And actually on this topic of detection, there's one online question from Jamin asking, you talked about interferometry, right? Where you have multiple telescopes and trying to all observe this one source. So how does it work? How are the images connected and how do all these telescopes work as one?
Good question. So, the way interferometry works is we need to think of light as being a wave. So a light ray coming towards us is a wave oscillating up and down and up and down. And what we need to do, if we have a big telescope, and one giant telescope, so this isn't interferometry, this is the real telescope. What will happen when we form an image of an object is the light from different parts of that image will come down to different parts of the telescope's mirror. So then imagine these waves coming down and then they reflect off the mirror and then they reach the camera. And depending on how far each light ray travels, you could imagine that each one of those waves is on a different part of its cycle. And that's what has the information that we need to contain the image. We call this the phase of the waves. It's which part of the up-down oscillation that the wave is at. So the way we do this with, a real big telescope combines the light for us. It reflects off different parts of the mirror and all gets to the camera at the same time. When we build an interferometer, what we need to do is we need to know exactly what phase the light was in when it arrived at the camera, so that we can work out if we had one big telescope that was the size of the Earth, how it would have combined into the single image. And this actually works best with radio telescopes, which is what the Event Horizon Telescope is using, because with radio telescopes, the frequency of the wave is quite low, which means we can build electronics. In fact, we have this electronic technology in our pockets right now. Our cell phones have exactly this technology, a radio receiver, which is able to measure the up-down of the radio wave. So the way the interferometer works is it records at each telescope the up-down of the radio wave as it varies over time. We store that. We also need to store a very precise measurement of what time it is when we make the measurement. So each one of the telescopes has its own atomic clock sitting next to it so that we can measure that wave over time exactly. Then we store all of that information, and then mathematically, we can combine all of that information together and make the image. It's a really remarkable technique.
Thank you. That was a really elaborated and detailed answer. Thank you. I see a hand over there.
What is it? You said like we have to sometimes couldn't like the scientific test because like each let's just say the sample the one that calculate that wrong. You can calculate what happens at the same time. At some point, we made a mistake, and the picture could get distorted.
Yeah. I'm still absorbing your question, but that's a really brilliant way to take it. Okay, so If I understand correctly, you're asking, you know, if we have a black hole and it can distort light, right? Or whatever light sources is at the back. But then if we make a wrong calculation, there could also be, you know, that kind of a distortion. So how do we know it's, you know, the black hole causing it, or it's like some mathematical error?
Yes, that's a really good question. So this is, I guess, there's two ways to see this. On one hand, this is a problem that that the black hole is distorting the light. So the light coming from different places as it passes past the black hole will arrive at different times. It gets delayed by the black hole and it gets bent around the black hole. So there could be mathematical errors there that we confuse with being the black hole. But actually there's also a lot of information there as well, because every bit of space around the black hole, the light coming to us takes a different amount of time to get there, and it gets distorted in a different way. So if we can actually measure what time the light arrives and how it's been distorted, we can kind of work backwards. And it's kind of a slow and careful process. So what we do is we have our measurements, and then we come up with an idea, a theory, or a model of what the black hole is doing. We compare that to the measurements we've got, and then we work out which bit were mathematical errors and which bits were real. And then we go backwards and forwards a few times until we think we've ironed out all the errors. And then what's left, hopefully, is all the information we want to be able to map out what's happening around the black hole.
That's a great question, and fingers crossed that we got it right. Okay, one last question from an online audience member, Tim, asking, well, all this mass that is being plunged into the black hole, as you mentioned, how is the mass communicate with each other in the form of gravitational attraction?
Ah, good question. So I guess the question is how the gravitational attraction gets communicated before it falls into the black hole. So that is actually through, and then I guess after it's in the black hole as well. And actually this is a really interesting question, and it was part of the motivation, if you like, for Einstein's theory of gravity. So before Einstein's theory of gravity, we had Newton's theory of gravity, which treats the gravity as being a force that's between different objects. We have other forces between objects. Electromagnetic forces are one of them. That's the force that's stopping me falling through the floor right now. It's the force that's exchanging light between all of us. Electrostatic forces, electromagnetic forces, happen because the particles exchange another type of particle between each other called photons. So these are like little messengers that go backwards and forwards between the particles. And that's a very well understood theory. But the problem with Newton's theory of gravity is that it doesn't account for the communication of the force in such a way. There's no time in Newton's gravity. So what that says is that, imagine you're at the edge of the solar system, somewhere near Pluto, and suddenly the sun disappeared one day. We won't worry about how the sun can disappear, but just imagine it does. In Newton's theory of gravity, at the edge of the solar system, we would know instantly that the sun has disappeared. But or even if the sun had moved, we would know instantly that the sun had moved because the direction, the gravity from the sun is pulling us will have changed. And that's a problem because Einstein's theory of special relativity says that nothing can travel faster than the speed of light, and we can't communicate across the universe faster than the speed of light. So at the edge of the solar system, we're not allowed to know instantly that something about the sun has changed. So we need some way of the force of gravity traveling, being communicated from the sun to the planets. And in general relativity, this all happens through space itself. So general relativity says that gravity as a force exists because the mass of the sun causes space and time to curve around the sun. So imagine space now as being like a rubber sheet. We put the sun into the rubber sheet and it creates a dent. And then when things try to travel across that sheet, they will end up being pulled around the dent. They'll fall into the dent, and it appears that they're being pulled towards the sun by the force of gravity. So in general relativity, the gravity is communicated just by the material moving around, curving space around it. And then as space changes, that changes the force of gravity. That's how John Archibald Wheeler actually summed it up very nicely by saying that matter tells space how to curve, and space tells matter how to move. That is general relativity in a nutshell. Now, if you're a quantum theorist, that won't be a satisfactory answer. Quantum theorists like having these particles that things can explain. And there are theoretical ideas of a particle called a graviton, like a photon, that could communicate the force of gravity in the quantum world. But we don't have a solid theory of exactly what a graviton is yet. So watch this space.
Thank you, Dan. We'll take one more question. Okay, over there, you. Yes. Oh, okay. Tricky question for you, Dan. What's on the other side of the black hole?
I like it. Finishing with the hardest, or maybe the best question. So what's on the other side of a black hole? Well, it depends who you ask. So the simple answer is that there is no other side of the black hole, maybe. The black hole is kind of this lump of material that collapsed to form the black hole, added to it everything that ever fell into the black hole. So what you end up with there is just this very dense lump of material that's just been crushed more and more and more until it's been crushed so much that it's so extreme that it defies our current understanding of the laws of physics. Now, I guess is it white? Maybe actually. So it'll be pretty hot. It'll get pretty hot. But that's kind of the boring answer to the question. The more exciting answer to that question is there are other things that can happen if we go back to this idea of gravity and general relativity as dents being created in space by matter. The black hole is when we have a very dense lump of matter. So instead of making a gentle dent in space, it makes this big well, like this big tunnel into space. So if the tunnel goes into space, maybe it comes out in another part of space or space in another universe. There are theories that a black hole is related to a similar object called a wormhole, where sort of two black holes join together. And they're actually a tunnel from our universe into either another universe or just another part of our universe. There's a lot more we could say about that. There's a whole fun world of wormholes and the theories around them, but I will leave that for another day.
Great. Well, thank you very much, Dan. And I know there are so many other questions that we didn't really get to. Dan will be here even after this talk, so please do talk to Dan and answer, ask all the questions you have. So let's give Dan another round of applause.
Thank you.
All right, so we are going to wrap up the event by just sharing a little bit about what's coming up. We had a pretty eventful month last month in April, and the public lecture this time will be the only event we have in May. But in June, we are planning a public stargazing night during the week of June the 3rd. Hopefully, there's going to be some clear nights, and we would welcome all of you to join us at the Stanford Student Observatory. So sign up for our mailing list. We will get the notification out as soon as we know which day is the best. And then moving on, we are planning another public lecture talking about cosmology, specifically the beginning of the universe through the cosmic microwave background. So that one will be somewhere in late June or July. And finally, in the summer, we will have another outreach event in Spanish called Noches Astronómicas here at Stanford, and that will be specifically for Spanish-speaking students and families. So if you want to follow us and also see what's new with KIPAC you're more than welcome to follow us on social media. And again, joining us at the mailing list just to see what are other events that we offer. So I would like to thank everyone again. And let's also bring everyone back to the screen. We would really, really appreciate your feedback on our event. So tomorrow there will be another email sending to you, including all those upcoming events and also a very quick feedback form. And you can tell us what you want to hear in the future, and we will try to make that happen for you. So thanks again, everyone, and wishing everyone a good night.